Hello everyone, my name is Xiang Fei from Tsinghua University, Beijing, China. In next 10 minutes, I will introduce my paper. The title is Regu2D, Accelerating Vectorization of SpMV on Intel Processors through 2D Partitioning and Regular Arrangement. First, I will introduce the introduction of the paper. Sparse matrix vector multiplication, SpMV, is an elementary and necessary kernel in many HPC domain applications. Accelerating SpMV faces three main issues. The first is irregular data access pattern because of index load like AVI. The second is memory bandwidth. We can see that one multiplication of SpMV requires three load instructions, two of which access the matrix state sequentially without data reuse, as orange box shows. The third is the short vector problem on vector processors, or SIMV processors in other words. Due to the sparsity and irregularity of non-zero elements in some rows, the length of a vector register may not be fully filled. Let's to say the inner for loop. Excuse to fill iterations. There are many existing sparse matrix formats on vector processors. For example, COC sigma is a variant of ELL, and it aims to decrease the number of padding zeros, but still contains many of them. Besides, the best value of sigma is unknown. This slide shows other existing formats. Figure 2 shows a sparsity matrix example and the corresponding data layouts for some formats. Table 1 shows the optimization method of these formats, and Figure 3 is the evolution of these formats. The first is LBus. It is a very simple work. It arranges elements horizontally on the CSR format and computes them row by row without splicing. So it's more likely to meet the short vector problem, as the pseudocode shows. The second is VHCC. It uses splicing to avoid the short vector problem, as Figure 2 shows, but it introduces many reduction additions and also needs conditional branches to test whether some vector lengths meet the last element of one row after each multiplication, and then VHCC stores the results to the output vector. The third is CSR5. It arranges elements vertically to partly avoid reduction additions, and it cuts some long rows into several parts and needs additional operations to reduce them. It also needs conditional branches to store the results. The fourth is CVR. It is similar to CSR5. The key difference is that CVR guarantees to put all elements of one row in the same column and avoids to cut one row into several parts, so as to avoid reduction additions completely. But CVR also needs conditional branches to store the results. The fifth is Regu2D and is proposed by this paper. It arranges elements regularly to avoid conditional branches and use gather-scatter instructions to update the results. As a conclusion, the computation of SpMV can be divided into three stages: multiplication, reduction, and updating stage. And different element layouts decide the specific reduction and updating methods. An ideal approach should concern 3 points. 1. To decrease the number of addition operations during reduction and avoid using conditional branches whenever possible. 2. To avoid accessing lengths of a vector separately. 3. To use vector gather-scatter instructions in the updating state whenever possible. In this paper, we proposed Regu2D to alleviate the previous 3 points. In detail, we use 2D partitioning to alleviate irregular access, but it cuts each row into several parts and aggravates the short vector problem and needs to store the row indices several times, which results in large storage space. Thus, we use splicing to alleviate the short vector problem and use regular arrangement to solve the inefficiency of reduction and updating. Indices compression is used to decrease the storage space and the amount of memory I/O. First, I introduce regular arrangement. It means that we select n rows that have the same number of elements to be a group and arrange them vertically. Thus, each row needs the same number of FMA in the reduction stage. The regular arrangement is required to find as many groups as possible to cover the maximum number of rows and elements. We use a dynamic programming to find them. To increase the flexibility of regular arrangement, we set a threshold T1 and limit the maximum differences of the number of elements in n rows to T1, as figure shows. That's to say, not all the rows are involved by regular arrangement. This is the key difference with CLC sigma. The detail of dynamic programming is that let Fi be the maximum number of groups between the first I rows, and Gi be the minimum number of elements between the first I rows. Thus, there are two choices for each row I. Combine row I with the last n-1 rows to be a group or not, as the formula shows. After that, for those rows that are not to be combined, we compute them row by row as Airbus does. The second method is adaptive 2D partitioning. For 2D partitioning, we found that fixed size is not the best choices for every matrices. Because of various distribution of elements within different regions, the small sizes P and Q make some chunks contain too few elements to improve the dead access locality, while the large sizes represent the largest range of irregular dead accesses for other chunks and results in poor data locality as well. This phenomenon is especially evident for scale-free matrices. In these matrices, a small number of rows contain a great number of elements, as figure 1a shows. As a comparison, the matrix of figure 1b is more regular. In this work, we propose adapting 2D partitioning. That to say, after 2D partitioning with fixed size P and Q, we merge a Johnson trunk horizontally to form a large trunk, but two rows need to obey. The first is only the trunks that hold too few elements need to be merged, and we don't merge two trunks that distribute too far. Figure 5 is an example. Each box represents a trunk. We assume that T2 equals to 20, and the maximum span of each block does not exceed 4 chunks. Thus, because of the first row, block 3 cannot contain the next trunk, and block 1 cannot contain the fifth trunk, limited by the second row. The third method is indices compression. It is very simple and decreases the storage of row indices. To do this, we renumber the row and column indices starting at 0 within a trunk, and compress these two indices into an int type. The size of trunk P and Q need to ensure that log P multiplied log Q not larger than 32. This is the compression rule during 2D partitioning. The fourth method is load balancing. The previous 4 works allocate all the elements evenly to each thread. This is not the best strategy. Figure 6 shows the statistics of execution time and the number of scattering instructions of matrix with multiple threads. We can see that different threads have a different number of scatter instructions, results in different execution times, and the trends of them are basically the same. So the number of elements and the number of corresponding rows both need to be considered during load balancing. In detail, we count the number of rows of the output vector for each thread and use it as a weight to readjust the computation loads of each thread based on the experience. Next, I will introduce the experience. The platform is Intel Xeon processors with AVX512 SIMD instructions. We use 13 scale-free and 16 HPC sparse matrices. We compare all work with Airbus, CVR, CSR5, and CLC sigma. Figure 9 shows the G-flops performance of each works, and the table lists the speed up of Regu2D compared with previous 4 works. We can see that Regu2D achieves an average speed up at least 20% for scale-free matrices and achieves an average speed up at least 34% for HPC matrices. For the effects of different optimizations on performance, Figure 8 gives the details. We set Airbus as a baseline. For 2D partitioning, it degrades 15% of the performance on average because of a serious shoot vector problem. So simply adopting 2D partitioning does not accelerating the SpMV. Next, regular arrangement improves 38% on average because it avoids the shoot vector problem and makes the computation more regular. In detail, it decreases the number of branch instructions and the branch miss rate. Besides, the number of store operations is lower than that of LBus and CBR because we use both scalar store and vector scatter instructions. For adapting trunk merging, it improves 5% on average, and load balancing brings 9% accelerating. Indices compression brings 13% speed up on average. As a whole, all the optimizations improves 49% overall in 7 representative matrices. Pre-processing is also important for SpMV. The original format is a matrix market format, that is, COO column measure COO format. Regu2D write back the date of the entire matrix twice after 2D partitioning and regular arrangement. So, on average, Regu2D costs 1.5 times longer than that of LBus and CSR5. SpMV will literature hundreds or thousands of times, so the larger pre-processing overhead will be optimized. As a conclusion, in this paper, we analyze 3 issues of accelerating SpMV, that is, irregular data access, the short vector problem, and the memory bandwidth. We proposed Regu2D and used 4 methods to solve them. We use adaptive 2D partitioning to increase the data locality, the range of regular arrangement, the vectorization intensity, and we use regular arrangement to regularize and simplify the computation process. We use indices compressions to decrease the amount of memory I/O and improve the load balancing by considering the number of elements and the number of corresponding rows both. We compare our work with 4 previous works and achieve almost the best performance. This is the end of my presentation. Thank you.